you, Abbas, for the introduction. I hope everyone can hear me. And hello to all the participants. First, I want to express my appreciation to the organizers for allowing me to provide the workshop with an overview of ongoing programs within the Department of Energy that are focused on critical materials. I am the director of the Critical Materials Institute, and CMI, as we call it, is supported by the Office of Electrical Efficiency and Renewable Energy through its Advanced Manufacturing Office. The Critical Materials Institute is an energy innovation hub with a mission to accelerate innovative scientific and technological solutions to develop resilient and supply chains for rare earth metals and other metals or materials critical to the success of clean energy technologies. We've begun our 9th year of operation as a public-private consortium. It's led by the Ames Laboratory, which is where I'm located, with 3 other national laboratories, 15 universities, and 27 private sector team members. As one of the earliest efforts to address supply chains of critical materials, in particular rare earths, we have developed and deployed innovative low carbon footprint solutions for mitigating supply chain risks associated with rare earths and lithium, cobalt, and graphite for lithium-ion battery storage. Well, I would love to tell you all about CMI's ongoing R&D efforts and our successes. For today's presentation, I was asked to speak about DOE's critical materials programs. So given my limited time, DOE has a lot of programs, but I will focus specifically on activities from within 2 offices within the Department of Energy, the Advanced Manufacturing Office and the Office of Fossil Energy and Carbon Management, or FECM. There are other programs that also focus on critical materials, including the Office of Science and Basic Energy Sciences, other applied offices in both EERE as well as ARPA-E. Together, these programs represent a national program of R&D that spans supply chains from mining and exploration to manufacturing and end of life, and from fundamental science activities to applied research and to demonstration and pilot scale facilities. So before I speak about the specific programs within the AMO office and FECM, let me comment more at a higher level on DOE's overall critical material strategy. The strategy is built on 3 approaches that combine and address supply chain risks along the supply chain with the aim to develop robust and resilient supply chains in a safe, sustainable, and environmentally just manner. The example to the right is a high-level illustration of the supply chain for rare earth elements. It's been broken down into kind of upstream activities, midstream activities, and downstream activities. And there's a color coding that indicates those activities where the U.S. has current capacity, green, and where there is limited capacity or no capacity, yellow and red, respectively. The first strategic approach is to diversify supply, and I think that's what this workshop is really focused on, identifying and unlocking conventional as well as non-conventional sources. And in doing so, increase the quantities of critical materials available, not just for clean energy technologies, but for all technologies and for national security. Exploration and cataloging of new sources is an important component, and DOE does coordinate with USGS to identify both new geologic sources as well as unconventional sources, including mine wastes and tailings. The second is to reduce usage of critical materials by discovering and deploying alternatives or substitutes. While normally thought to consider substituting a new material for another material that has reduced or no critical materials, you veterans of the COLA wars know that that is not done without some degree of what do you want to say, acceptance for the difference. So Pepsi is not Coke and Coke is not Pepsi, and The same thing applies when developing a new material to substitute for an existing one. There are always trade-offs, isn't there? So the approach, it can go beyond just that. We can replace an element for an element. We can place a material for a material. We can replace a process for process, and we can replace a device for a device. And therefore, developing substitutes actually is a strategy that applies throughout all of these stages of the supply chain. And I think the last talk, Jen was talking about a new process to concentrate rare earths and lithium, nickel from very dilute solutions. Ashley said it very well earlier in the workshop. These are low quantities, but abundant sources. So how do you bring the economics? How do you concentrate with fewer steps? How do you intensify the processing? So substituting new processes for old. The third approach, which applies across the supply chain also, is to reuse and recycle and make more efficient use of not only the critical materials, but all the materials and chemicals, reagents that are used in the various processes to take something from the source, the raw material source or raw mineral source up through a finished product. This approach is generally based on circularity principles and can represent an unconventional source for some critical materials that actually is a significant source compared to raw materials from primary sources. So let me go to the Advanced Manufacturing Office and their critical materials R&D program. AMO supports RD&D activities along all of the supply chain stages that I just talked about, incorporating all three approaches. AMO has a number of programmatic activities shown in the figure to the right. The Critical Materials Hub, the Institute is central to that. And we focus specifically on clean energy technologies. What materials are going to be needed to be able to decarbonize transportation, to develop wind energy, wind generation, solar generation. AMO generally supports early stage RD&D projects. If you're familiar with technology readiness levels, these are TRL 2 through 4. That couples very well with the early or fundamental science that is funded by the Basic Energy Sciences part of DOE. And we do coordinate at the other end with STTR, SBIR, and other programs that allow AMO to scale lab-proven technologies from these RD&D programs out to demonstration and pilot scale activities. Earlier in FY 2021, AMO completed a funding opportunity and awarded $50 million to 15 different projects. The project focused on both rare earths and lithium and were broken into 2 categories. 4 projects were selected to validate extraction, separation, and processing technologies at a demonstration scale, and 11 early stage projects developing new methods for upstream and midstream stages of the supply chain. These projects leverage CMI's capabilities and expertise, and we will be expected to coordinate over the next couple of years with these programs. In addition, AMO has established a lithium R&D virtual center to coordinate activities to increase domestic supplies of lithium from a variety of sources, encompassing both hard rock, clays, and brines. The demonstration and pilot scale projects are targeting those stages of the supply chain where the US does not have or has limited capabilities. For permanent magnet supply chain, the goal of the AMO pilot scale projects is to demonstrate separations of mixed rare earth oxides available from both conventional and unconventional sources, like the sources that Jen just talked about. Using novel and advanced technologies at a production scale of 15 tons, for example, of neodymium praseodymium oxide that is whose target is to enrich and concentrate to a 99.5% purity, i.e. those purity levels that are required for the production of permanent magnet alloy. In the lithium space, 2 projects are focused on direct processing for lithium hydroxide from claystone resources. One project will combine a number of processing methodologies to develop the flow sheet to produce lithium hydroxide precursor. Most processing today produces an intermediate carbonate that then must be converted to hydroxide, which is usually an energy-intensive roasting process or calcining process, or involves a calcining process. The goal is to demonstrate a throughput of up to 5 tons per day. The second project looks at geothermal brines as a potential source of battery-grade lithium hydroxide. The third pilot scale project focuses on graphite. Graphite is a critical material, but it doesn't capture as much or the same attention as lithium has, but it's just as important as it's the anode material of choice for the lithium-ion battery. US has few natural graphite sources, but none are currently actively mined. Synthetic graphite has been gaining attention as a substitute, but generally is produced by a highly energy-intensive process. This project looks to reduce the carbon footprint at a scale of about 200 kilograms per hour. Turning to the Fossil Energy and Carbon Management Program, FECM has established a Mineral Sustainability Division whose vision is to promote an environmental and economically sustainable critical material and carbon ore resource recovery industry in the United States. Its intent is to support clean energy job growth in domestic industries, as well as environmental and social justice stewardship through co-production and reclamation-based research and technology development. The division will work to support the US transition to a carbon-free economy and support a domestic clean energy manufacturing industry through characterization and assessment of domestic critical mineral and carbon sources, which I think you have heard something about during this workshop, development of advanced resource extraction, processing, and extractive metallurgical technologies, which the last talk talked a little bit about, and evaluation of the co-production potential of critical minerals and carbon ore from high-value carbon products. Like AMO, it has a multiple of different approaches to its RD&D. There are small-scale projects shown in this illustration on the left, a coal ash product at PSI, Physical Sciences. West Virginia University has built a pilot program, and I'll discuss a little more about that later. The University of Kentucky, a refuse pilot, and finally North Dakota with a lignite project. These small-scale projects were designed to demonstrate the technical feasibility to produce rare earth elements and other critical materials from unconventional sources such as lignite, coal ash, acid mine drainage, and refuse. They began in 2016 and by 2018 began to produce mixed rare earth oxides. In the last 2 years of the project, went from producing grams to kilograms as shown in the table, and projected material to be produced through 21 and 22. While demonstrating the feasibility to produce mixed rare earth oxides, these projects have also been increasing the purity of the mixed rare earth oxide being produced up to the target value of 99%. The results from these small-scale projects inform a larger set of projects called pre-feed projects. These projects will produce between 1 to 3 metric tons per day of mixed rare earth oxides or rare earth salts and other critical minerals. The 13 projects that were recently selected for the concept phase of the pre-feed studies and the 8 projects in the table on the right were selected to perform more detailed research studies. These projects will address technical issues, provide conceptual design for a 1 to 3 metric ton per day facility, explore the CapEx and OpEx needed to operate those facilities and produce mixed rare earth oxides. As you can see on the table, there is a diversity of feedstocks being utilized in these studies and different types of processes, feedstocks, scalable products, all incorporated into the business models. And I think that's a hallmark of the work that DOE does in this space, is we do look at the techno-economic models as well as life cycle analyses as we develop these R&D programs to be able to assess the feasibility of these being moved into the commercial sector. As I previously mentioned, co-production is the key. The table at the bottom of the page includes potential byproducts, co-products associated with the 13 concepts. These projects will provide the information needed to inform future FEED studies for environmental sustainable production while optimizing circuits for co-production and cost reductions. As I mentioned, it's not just critical materials that the FECM program is interested in. There are 60 billion tons of coal refuse from 200 plus years of mining. They all have high carbon content that enables lower cost of productions for carbon fibers compared to petroleum-based precursors. And they can be used in construction products and cements, which lower GHG emissions. The next generation construction and infrastructure materials could be made from coal-derived sources in products such as bricks, roof tiles, concrete, and these are competitive or even lower cost compared to the state of the art. So everything comes together under the FECM in the core CM, the Carbon Ore, Rare Earth, and Critical Materials Initiative, where the primary objective is to build coalition teams that consist of private industry, university, state, local, and federal government personnel who can develop and will develop and implement strategies that enable each specific U.S. basin to realize its full economic potential for producing rare earth, critical materials, and high-value, non-fuel, carbon-based products from basin-contained resources. The initial rollout is in basins associated with energy and co-located with economically stressed communities in need of clean energy jobs and downstream manufacturing of high-value, non-fuel, carbon-based products. Again, the projects will address the regional technical and non-technical challenges, because we know these types of challenges can vary from state to state. The initial projects have over 130 different participants that will make up these coalitions that come from academia, private industry, local, state, federal, tribal personnel, to develop strategies that are unique for each of these basins. These projects will provide the foundation for educating next generation technicians, skilled workers, and STEM professionals. And it will be conducted in 3 phases: an initial assessment and planning phase, followed by a complete assessment and developing and initiating strategic plans, and then finally implementation. So together, these projects will address resource assessment for critical materials, rare earth elements, and carbon, strategies for reuse of waste streams, strategies for infrastructure and businesses, technological assessment, development, field testing, technology innovation centers, and stakeholders, outreach, and education. That's the set of prepared slides I have. I'm happy to address questions. I refer to the Advanced Manufacturing Office and Fossil Energy and Garbage Management. I list their contacts, technical program managers for the critical materials here, but I'll do my best to answer the questions that I can. Thank you.